Back in high school, the seniors and I were tasked with building an end-of-year project. It has to be some sort of factory that assembles something, combining everything we learned over the course of the 4 years into one project. My team decided to build a drone factory. One of my tasks was automating the CNC machine to machine out the base frame of the drone, which you've already seen in an older video. The other task was to make a cell that assembled the top half of the drone to the machined out part from earlier. This was basically just a pick and place operation. So my thinking at the time was I just needed a robot that can pick and place light parts. There are a couple robots in the industrial world designed to do specifically this. One of those is a SCAR robot, which is a selective compliance assembly robot arm, designed to manipulate parts fast, accurately, over a decent amount of workspace. But I wanted to build something more complicated, so I went with a Delta configuration. Some call it spider robots, that's kind of what it looks like. They're very fast, accurate, and they're just really cool. This was part of one of my last videos, the soldering factory, where I used the Delta robot to feed the material to the Mirabot. Okay, so going on in the control box is just a 12-volt power supply, supplied by 120 volts AC, and that outputs 12 volts, which goes to 3 different DC-DC converters. The 6 volts is for the servo motors, the 9 volts is for the Arduino, and the 3 volts is for the LEDs. I'm using an Arduino Uno as the microcontroller here, and that connects to the computer via USB. I have a Arduino CNC shield controlling the 3 axes, the 3 stepper motors, and then all the power through the motors goes through the e-stop button. Here is the CAD model. The 2020 extrusion holds up the frame of the robot, and that seems to work pretty well for how light it is. And then the whole framing for the robot is just one part, which is a horrible idea and made assembly just a pain. Ideally, this is going to be in pieces that are assembled with the robot, but I was short on time, so there is no way to tension the belts. The way the belts would be initially tensioned is there's a hole in the belt, and it bolts through the belt into these self-tapping holes, and then it goes around the pulley, and you do the same thing on the top, just pulling it as tight as you can. By far the most challenging part of this robot was the kinematic model. How the kinematic model works. I can't explain it all the way because I've forgotten at this point. But essentially, this arm moves, and it goes to this joint down to the end effector. So as this moves, you have a different distance between the center of the joint and the center of the joint on the end effector. So if you do that for 3 motors with a difference of 120 degrees, so you have 3 different arms in a circle, then you can give an X, Y, Z coordinate. And the algorithm that does this, you import an X, Y, Z you want it to go to, and it will give you the angles of each arm. Now, of course, this program is available on GitHub if you want to use it for your Delta robot. All the math is done right here. Now, technically, this robot is a 5-axis. I mean, you got your wrist and the gripper, but I guess that's usually just called a 4-axis. Gripper doesn't count. I didn't spend a lot of time refining the program or the way you program it because I didn't have a lot of time. This chunk of code gets it to move. So you can tell it to calculate the angles, given your X, Y, and Z, and then using the Excel stepper library, you can do move to commands for each of your motors with your corresponding angle, and then multiply that by this is compensating for the mechanical advantage in the pulleys as well as the steps per revolution. And I only remembered that because I left a note. Notes are very important. You should keep notes. And so with your angle set to each axis, you need to run those, and with Excel Stepper, a program a line like this in a while loop is going to run all three of your axes at the same time until they're finished. So I didn't take any footage of the robot operating in the line, which I wish I had, but this is basically what I came up with. Remember, I only had a month to build this, so please excuse the non-industrial grade mechanical design, along with the fact there are just no proper connectors, so it's permanently connected in the box. If I had to redo this project, I would change a lot, pretty much everything. Down to the way, especially how the belts are tensioned. That's a pretty stupid design. But the idea is it just had to work, and I had a month to do it, and it worked. So I was pretty happy with it. With that being said, as per usual, all the CAD and code is on the GitHub in the description if you want to take a closer look at it.